Alright, in this video we're going to be looking at questions 18, 19, and 20 on the Spring 2016 Semester Exam Review. So let's start with question 18, which is looking at graphing polynomials. So the information you're given in these two problems are a polynomial equation in factored form, and you're being asked to sketch a graph. So when our equation is given in factored form, we're given a lot of information that's going to help us graph it. However, in order to get started, the very first thing we want to identify is what is the basic shape. And in order to get the basic shape of what our graph is going to look like, which is going to determine our end behavior and things like that, we need to know the lead coefficient. So we want to find the lead coefficient of the equation. The lead coefficient is just basically the x term to the highest power. So to do that, all we have to do is multiply all of the leading terms in each factor together. So for problem A, our lead coefficient is going to be x times x squared. Notice that that last factor was squared, so we have to square the x. And so that is going to give us x to the fourth power. Now there's two things we're looking at here from the lead coefficient to help us determine our basic shape. The first one is the degree. And so the degree of this polynomial is 4. And so anytime we have an even degree polynomial, then that means that the ends are going to point in the same direction. Okay, the second thing we're going to look at is the sign of our lead coefficient. And in this case, our sign is a positive. So if we're positive, that means we're going to be pointing upwards. So our basic shape, we don't know what's happening in the middle, but we know that the ends are going to be pointing up. So the middle could have lots of curves in it, but the ends, both ends will be pointing upward. Okay, so now we're going to use the rest of the equation to help us determine some other important stuff. So the next easiest thing for us to find is going to be the zeros. And that's basically what the factors give us. So our zeros are simply each factor set equal to 0. So as an example, if I say x plus 2 equal to 0, I solve for x, I get x equals -2. So notice that the zeros are simply the same number in our factor, just the opposite sign. So our zeros then are going to happen at -2, +3, and a +1. Now I know these aren't in numerical order, but that's kind of in the order that they're listed in the equation. So also notice that the last factor is squared, so that's going to give us a special factor. That's what we call a double zero. And if you remember back from what we learned about double zeros, it creates a turning point at that 0. So you're basically going to treat that 0 like it's a quadratic where the vertex is on the x-axis. So that's going to be a turning point. Okay, it's either going to be a max or min depending on how we are approaching the 0 at that point in time. Okay, so the last thing that we need to know is we also need to know where we're going to hit the y-axis. So we need to find the y-intercepts. And we're simply going to do that. We're going to take all of the constants in each factor and multiply them together. So I'm going to have a 2 times -3 times the -1, but keep in mind the -1 is squared. So if I multiply those together, 2 times -3 is -6. -1 squared becomes +1, so my y-intercept happens at -6. The reason this happens is because the y-intercept is when x is 0, so if we plugged in 0 for all the x's, we would be left with those numbers. Alright, so now we have enough information to sketch a graph. What I'm going to do first is I'm going to label all of my intercepts. And when I label all my intercepts, I'm going to kind of get dots that look like this. So it doesn't look like a whole lot yet. But now I'm going to take my end behavior and notice that at the edges of my graph, my arrows should be pointing upward. So if you want to kind of draw preliminary little arrows in there, those are going to be upward. So to trace my graph, what I'm going to have to do is I'm going to have to connect those arrows, but I have to go through every dot that I've already plotted on my graph. Keeping in mind, again, that this -1 dot, I'm going to not pass through it, I'm going to turn around at that. So I'm going to cross through the -2, and then in order to get through this y-intercept at -6, at some point I'm going to have to turn around. And then when I approach the +1, 0, I'm going to hit it and turn. And then in order to go back through 3, I'm going to have another turning point. and then I'm going to connect my with the right side in behavior. So notice it creates kind of a W shape, which is a somewhat classic x to the 4th power shape. And the big thing is that you make sure that -1 or that +1, 0 becomes a turning point. So let's do the same thing over here with question B. So our lead coefficient, we're going to simply multiply all of the x terms together. Keeping in mind the last one is squared. So this time I get a -x to the 4th. Okay, so that's going to determine two important things about my end behavior. Since my degree is still 4, I know the ends are going to go in the same direction, but now my sign is negative, so that means the ends are going to point down. So my end behavior then are going to have two ends that point down and then something happening in the middle. It could be a simple one turning point, or it could be kind of our W shape, which I guess in this case would be more of an M shape. Okay, so we're probably going to have an M shape in the middle. So now let's identify our zeros. Remember those come from just simply the setting each factor equal to 0. Now, an important thing when you're setting your factors equal to 0, this first factor, -x, when I set it equal to 0, anytime you have x by itself or a -x by itself, that means you're going to have a 0 at 0 itself. So you're going to go through the origin when x is a factor on alone. So we're also going to have zeros at +3 and -2, and again, because the -2 is squared, that's going to be a double 0 or a turning point. So however you want to kind of identify that in your notes to help you remember to do something special there. And the last one is the y-intercept. So notice that the first factor of -x doesn't technically have a constant. It's really -x plus 0. So when I multiply my constants together, I have 0 times -3 times a +2 squared. So no matter what all my other numbers are, because that first factor has a constant of 0, that makes my y-intercept 0, which makes sense. If I have to cross through where x equals 0, that's also that's at the origin. That means y is also 0 at that point. Okay, so now let's go ahead and plot those zeros, the intercepts, on our axis. So this would be with my 3 x-intercepts, and then my y-intercept happens to also be through the origin. And I remember that from the end behavior I found at the beginning of the problem that both ends are going to be going down. And keep in mind, remember again, that -2, 0 is going to be a turning point. So when I draw my graph in, the first thing I get to is that -2 intercept, so it's going to turn around there. In order to go back through the origin, then I'm going to have to turn around somewhere between -2 and 0. And then in order to go through my next 0, I'm going to have to turn around somewhere between those and then connect it to my other end behavior. So again, we kind of see that W or M shape creating our quartic graph. All right, so let's go ahead and move on to rational functions. And so each question under rational functions is asking you for a slightly different piece of information. So in the first one, we're asked to find the domain of the function and to describe the different types of discontinuity. So let's start with the domain. That's going to be based on the denominator. So what I have to do is I have to be able to see more details in my denominator than what I have. Same thing with discontinuity is going to come from the denominator. They kind of go hand in hand. But before I can do anything to determine specifics, I have to factor it. So the first thing you're going to do for each of these is factor them. A is going to be a little easier to factor. B, because it has that leading coefficient of 2 on the numerator, is going to take a little more thought. But we're going to factor. I'm going to go ahead and factor both of these equations now. All right, so this is what each equation looks like in factored form. And you always want it in factored form in order for this portion in order to determine your domain and your discontinuity points. So the domain of the function is, rational functions are always going to be all real numbers, except what you can would turn the denominator into 0. So remember that the denominator cannot equal 0. Okay, so whatever number we put in for x cannot create a 0 as a factor. So in order to find what values to exclude, we would just simply set each of those factors in the denominator equal to 0. So for instance, x plus 1 equals 0 would give me x equals -1. So that's what x cannot equal. So first we would say the domain is all real numbers, and then we would say x cannot equal -1. From the second factor in that problem, x cannot also not equal a +1. So if you were to put either of those numbers into that equation, you produce a 0 on the bottom, and you can't do that. Okay, so for the second problem, our domain, again, is going to be all real numbers, but our two excluded values, this time x cannot be a -2, and x cannot be a +3. Okay, so that's first is the domain. You take what would turn the denominator into 0 from your factored form, and that's what you exclude. All right, so the next thing we're looking at is discontinuity. Discontinuity are going to be represented by any kind of breaks in our graph. And there are two types of discontinuities that we're going to see with rational functions. They can be vertical asymptotes, or they could be a hole in our graph. Okay, so they both, again, come from the denominator, and those values that are producing 0 factors in the denominator, but it's all dependent upon what we see or don't see in the denominator. So let's start with A. So if we look carefully at the equation in A, I notice, before I do anything else, that I have the same factor in the top and the bottom. So what happens is I can cancel the x plus 1 out, and it would simplify our equation to x minus 3 over x minus 1. Now notice, I still have to exclude that the x plus 1 still produces a break in my graph where it cannot exist because it was in the original equation, but in my new equation I don't see it. So when a factor cancels away, what happens is it produces a hole. And a hole is going to happen anywhere where x equals the number that has already canceled out. So we're going to have a hole in our graph at x equals -1. Our vertical asymptotes, however, are going to be based on whatever factors are actually remaining. So this x minus 1 is going to produce our vertical asymptote, and that's going to happen when x equals +1. So notice the two values that I used to exclude in my domain are either going to be a vertical asymptote or a hole when we describe the discontinuity. Okay, so let's look over here at problem 2. If I look back at the equation, I see that I have no common factors in the numerator and the denominator, so nothing's going to cancel out. That means both of my factors in the denominator here are going to represent vertical asymptotes. So my vertical asymptotes are going to happen when x equals 2, as well as when x equals, -2, and when x equals +3. So if you don't cancel the factor out, it will be a vertical asymptote. If the factor does cancel out, it produces a hole. Both of those are discontinuity or values that cannot exist in our domain, so both of those numbers have to be written as part of our domain exclusions. The last thing we're going to look at is question 20, and question 20 is asking us to describe the end behavior of the functions. Now what's nice about describing the end behavior of rational functions is we don't need to factor it, which is good because some of these are some complex looking. All we need to know for end behavior, just like we did with polynomials when we were looking at which direction did the ends point, we need to focus on the lead coefficients. Now because this is a fraction, we're going to have a lead coefficient in both the numerator and the denominator. So remember, a lead coefficient is going to be your highest power. So the first thing I recommend is going in and circling your term of the highest power. Now, it's not always going to be the first term in your in that section. So notice in part B, my highest power is the minus x squared at the end. So first, identify the lead coefficient in both the numerator and the denominator. And what I'm going to do is I'm going to rewrite my equation so I'm only focusing on that lead term. So this first equation becomes y equals 5x squared over x cubed. And the reason we're doing this is because we're eventually going to plug infinity in for x. And if I'm comparing x squared to x, infinity squared is going to be so much more larger or powerful than just regular infinity that we kind of just disregard everything else. Okay, so we're just focusing exclusively on the lead coefficient. Now what we're doing here, so let me go ahead and do that for the next ones. 2x squared and over negative x squared. And the last one would be 2x cubed over 4x squared. Okay, so now that we have that, you can at this point simplify what you have. Since we have x's in both the numerator and the denominator, we would get in the first one 5 over x. The second one becomes -2 because the x squares cancel out entirely. And on the last one, it becomes x over 2, because the 2 over 4 is 2 over 2, and the x cubed is on top, so it keeps the x in the numerator. So for each of these, what we're going to do at this point is we're going to consider what happens as x goes to infinity, because that's what our end behavior is. What is happening to the right side of the graph, or the left side of the graph, as x gets infinitely large. So as x goes to infinity, that's what we're looking at on each of those. We're kind of seeing the limitations of our graph. So what we're really doing is we're plugging infinity in for x. Okay, and so this one would be infinity over 2. No, okay, so let's talk about each one of these. So in part A, when I plug infinity into my equation, it's being divided. So if you think about it, if I have 5 over a million, it's getting really close to 0. So if that million goes to infinity, then it's going to get closer and closer and closer to 0. So what happens is as x goes to infinity, y goes to 0. Y becomes a value really, really, really close to 0. Okay, never actually equals it, but it gets really close. Okay, so my end behavior on this would be y equals 0, or y goes to 0. This is very similar to what you've learned in the past of your horizontal asymptotes. Okay, in part 2, as x goes to infinity, if I look at my equation, there's no more x remaining because it canceled each other's out. So y is simply going to approach whatever number I have there. So if I plugged in infinity, I still get negative 2. So y is going to level out at negative 2. And then on the last one, when I plug infinity in, I get infinity in the numerator. Well, it doesn't matter if I divide infinity by 2, it's still going to be infinitely large. So in this case, y is going to approach infinity, which means it's going to keep increasing without any boundaries. Okay, so these are kind of the equivalents. This end behavior is the equivalent of what you learned about horizontal asymptotes in the past. But we're using a more mathematical concept in order to help you determine. So again, define your end behavior. Just focus on your lead terms, simplify your fraction, and then plug in infinity for x and see what happens, and that's going to produce your answer.